All right, so today we're going to be talking about parametric equations. We've had a little bit of experience with parametric equations when we talked maybe about like systems of three equations with an infinite number of solutions, and you'd write the pattern. I know I always introduce that as infinite number of, I'm sorry, as a parametric equation when I do that. So consider throwing a ball, right? As you throw a ball, not only is it traveling up and down, but it's also spanning a horizontal distance as well. So at each different time, the ball is located in a different position, having a different x and y coordinate. Furthermore, the action of throwing a ball has a vertical and horizontal effect on the ball. We can graph this event telling where the ball is located and when the ball is at a given point on its path. The variable t is called the parameter and gives the various times for the ball's location. The equations that describe where the ball is located express both x and y as functions of t and are called parametric equations. The graphs of parametric equations, well, they're called plane curves. So as you throw this ball, right, we see this up and down motion that happens, and that happens as time passes. It goes up for a certain amount of time and then it comes back down. And similarly, in that same time period, we're seeing this horizontal translation happening as well because it's moving, forward. Parametric equations just say that we're going to split it up and we're going to describe what's happening to it vertically, separate from what's happening to it horizontally. So here's our official definition. Suppose that t is a number in an interval I. A plane curve is the set of ordered pairs x, y, where x is f of t and y is equal to g of t. So x is going to be one function of t, while y is a different function of t. And we can even see from this picture, the horizontal change is kind of like this straight line where our vertical change is up and then down. Our steps for graphing a plane curve, basically what we're going to do is instead of making an XY chart like we typically do when we're starting out to graph something that we're unfamiliar with, we're going to make a TXY chart. So we're just going to have like an extra column to our XY chart. You're going to select some values of t on the given interval. Then for each value t, we're going to use the given parametric equations to compute x and y, and then we'll plot the points x, y like normal in the order of increasing t and connect them with a smooth curve. Now, when you connect the points to form your smooth curve, you need to include arrows on your curve to indicate the direction of the graph corresponding to increasing values of t. We call these arrows indicating direction the orientation of the graph. So don't make this hard. So we want to graph x equals t minus 1 and y equals t squared, where t is in between -2 and +2. So we're going to make a txy chart. And we're going to choose values of t from the given interval. It's really important when they give you an abrupt starting and stopping point that we use that first and last point for t for sure. Now, in between, we can choose what we like. With this one, because we're only going from -2 to +2, I'd be inclined to pick all 5 integers in this interval. And then we're just going to take these t values, plug it in, get an answer for x, plug it in, get an answer for y, and then plot those points. I'm going to do all the x's first. X is defined to be t minus 1, so we're just going to take our t value and subtract 1 from it. And then we'll do the same kind of thing for the y. Y is equal to t squared. So for the y column, I'm just going to take my t value and square it. Any questions on how I'm getting those numbers in red? These 5 pairings of x and y values are the 5 points that we're going to plot to graph our plane curve. So -3, 4, -2, 1, -1, 0, 0, 1, and 1, 4. Any questions so far? All right, now it's time to connect these points to make our nice smooth plane curve. We want to start with increasing t. So my lowest t value, -2, was the point -3, 4. So we're going to start there and connect our points. And then it's important that we go back and put in the orientation to say where we started. And usually we put an arrow in between each one of our points. And there we go. Questions, anybody? All right, let's try another one. So we'll start by making our TXY chart. Here it says that t is greater than or equal to 0. So you'll notice it's giving us an abrupt starting point, but not a stopping point. So I just need to be sure that I start with that abrupt starting point, the smallest value for t, which is 0. And then I want to just choose any values of t greater than 0. You can choose whatever you like, but I would kind of look at my parametric equations and see if there are some numbers that are going to be easier than others. X is t plus 1, while y is the square root of t. So what kind of numbers would be good for us to choose for t, looking at how x and y are defined?
Probably ones that can be square rooted easily.
Yeah, one perfect squares, so that when we take the square root of it, we don't have to plot decimals. It's not wrong to plot decimals, it's just not as easy, so why not make our life easier when we can? Oh, let's choose 1, 4, and 9 to go with it. And now we're just going to find our x values and then our y values and plot those ordered pairs. I'm going to do the x's first. This time we're taking our t value and adding 1 to it. 1, 2, 5, 10. And then for the y value, we're taking the square root of our t value, 0, 1, 2, and 3. And now we have 4 ordered pairs to plot. 1, 0, 2, 1, 5, 2, and 10, 3. 0 is my starting, so I'm going to start at the point 1, 0, and then it extends infinitely beyond that. Here's our curve. And then we want to go back in and put our orientation arrows in to show the path of our travel. The reason our parameter, we use the variable t, is because we're just basing it off of time. Parametric equations are used a lot in physics applications, and things are almost always based off of time in physics. Questions, anybody? Okay. All right, we're going to practice now converting from parametric equations to rectangular equations. This is sometimes called eliminating the parameter. So you might see the directions say eliminate the parameter. What we want to do is we want to solve one of the equations for t. Now, preferably, we want to solve the x equation for t. Now, if it's just way too hard to solve the x equation, okay, fine, solve the y equation. But preferably, let's solve the x equation for t. Then you're going to substitute the expression for t into the other parametric equation. Okay, so I'm going to try to solve the x equation for t. That's not going to be difficult, right? All we need to do is add 1 to the other side. We get x plus 1 equals t. We're then going to take this x plus 1 and we're going to substitute it into our other equation for t. This is going to give us y equals x plus 1 quantity squared. And that's our rectangular formula. So that's why we usually like to solve the x equation if we can. So we plug it into the y equation, because typically in rectangular form, we like it to be y equals stuff rather than x equals stuff. Now, coming up with the domain can be a little bit tricky. There's a couple different ways that you can do it and a couple different ways you have to do it based on what the parametric equation looks like. Now this one would be easy for us to do because we were able to easily solve the x equation for t. They told us that t has to be between -2 and +2. And we were able to solve our x equation for t. And x is the domain value, so that's why I'm interested in the x. If I substitute that expression x plus 1 into our domain expression for t, we get -2 is less than or equal to x plus 1, which is less than or equal to +2. And then we can solve the sandwich inequality and get that x is in between -3 and +1. And this would be the domain in rectangular. Questions? All right, let's try another one then. We want to convert x equals the square root of t, y equals t minus 1, where t is greater than or equal to 0, into a rectangular equation. So let's start by solving our x equation for t. All we need to do here is square both sides, and we'll get that x squared is equal to t. We'll take this x squared and plug it into our y equation for t, and we get y equals x squared minus 1. So this is a good example of where just plugging this into here is not going to work for getting our domain. And I know the question isn't asking for the domain, but sometimes you're asked for the domain, so I just thought I'd bring it up here and there. If I plug x squared in, I end up with this polynomial inequality. Where is x squared greater than or equal to 0? Well, it's always greater than or equal to 0. But we know that that can't possibly be the domain. And the reason that can't possibly be the domain is go back and look at your x equation. X is equal to the square root of t. A square root is only ever going to spit out a positive answer. I guess it could be equal to 0 as well. So because your square root is only ever going to give an answer that's greater than or equal to 0, we can't just plug into this inequality. We have to think about it. Our domain is only going to be from 0 to infinity. So the domains for the going from parametric into rectangular, I think is the trickiest part of the whole section. Because there's not just a, oh, this is always the rule thing. Questions at all on that one? All right, let's try another one. This time we want to convert x equals cosine of t, y equals sine of t, where t is in between 0 and 2 pi, to a rectangular equation. When our parametric equations are defined in terms of trigonometric functions, we actually do it in a completely different way. So I'll outline it over here on the side for us in steps. So the first thing you want to do is make sure the trig function is isolated in each of your equations. Now for this one, it just so happens to be that way, so great. Next, we are going to square both sides of each equation. So our first equation is going to turn into x squared equals cosine squared. And our other equation turns into y squared equals sine squared. And this is a legal math move for us to square the left and right hand side of an equation. It's not legal for us to square the top and bottom of a fraction, but we can square the left and right sides of equations. Any questions so far? All right, well, next we are going to add the equations together. And you're going to be adding down, just like you did when you learned the addition technique for solving systems of equations. When we do that, we're going to be left with x squared plus y squared equals cosine squared plus sine squared. Do we recognize something now that we've added those together?
We have a trig identity.
We've got one of the Pythagorean identities. So now we're going to apply a Pythagorean identity. Because the way that you know that you're out of parametric is that you don't have any t's left. So we know we're not done because, we still have these t's. So applying our Pythagorean identity, cosine squared plus sine squared is equal to 1. We end up with the equation x squared plus y squared equals 1. And there is our rectangular equation. Questions at all? So the domain with this one, so you can do this one, but you can't really do all the trig ones. I probably have another. Yeah, you won't be able to do the next trig one because you don't know what the graph of this looks like. But you should know what the graph of x squared plus y squared equals 1 looks like. What is that?
A parabola.
Nope. Because both x and y are squared. So this is a circle centered at the origin with a radius of 1. This is the unit circle. If we go back and look at what they gave us for t is between 0 and 2 pi, and we know when thinking trig that that's 1 trip around the circle. So we're going 1 trip around the circle, and we end up with a circle, so that means, well, we want this whole circle. Really, you need to graph it to be able to get the domain, but we said that this is a circle centered at the origin with a radius of 1. So we would say that the domain is -1 to 1. Questions? All right, let's try another trig one then. We're going to go the same steps. Anytime it's a trig function, you follow those same steps. So step number 1 is to isolate the trig function. Well, that has not already happened for us in this example. So let's start with the x equation. We'll start by subtracting 2 and then dividing by 4. So that'll be x minus 2 over 4 equals cosine of t. Let's do the same thing for our y equation. We'll solve for the trig function. We'll add 1 and then divide by 3. Once our trig functions are isolated, now we're going to square both sides. I think I'm going to stack them so it looks like the other one now. So squaring my blue equation there, I do want to apply this outer exponent of 2 to both the numerator and the denominator separately. So we're going to get x minus 2 squared over 16 equals cosine squared. And then for our green equation there, I'm going to do the same thing. I'm going to apply that outer exponent to the numerator and denominator separately. And now we want to add these together. And that's going to give us x minus 2 squared over 16 plus y plus 1 squared over 9 equals cosine squared plus sine squared. And then lastly, we're going to use our Pythagorean identity. We know that cosine squared plus sine squared is equal 1. We end up with the equation x minus 2 squared over 16 plus y plus 1 squared over 9 equals 1. Questions?
So you know you're all done when you get rid of like the sine and the cosine.
Yep, no t's is how you know you're out of a parametric equation. So this one you guys would not be able to find the domain of because you don't know how to graph this. We'll do this in pre-calc. This is actually an ellipse, an oval. So we would need to draw the picture to be able to easily come up with what it looks like and to get the domain. Now I do want to mention, and I'll mention again in pre-calc, see how up here it says that t is restricted from 0 to pi? We know that that's halfway around the circle. So I said that this, if we graphed it, is an ellipse, an oval. But because t was restricted to the top half of the circle, our graph would only be the top half of the oval. But we'll talk about that more in pre-calc. I would definitely feel comfortable with giving you this type of equation to convert. I just won't ask for the domain for it. Questions to anybody on converting from parametric to rectangular? All right, well, now we're going to go the other direction. Given a rectangular formula, we want to find a parametric equation. This is probably the easiest thing you're going to do in math for the rest of your math life. There are infinitely many pairs of parametric equations that can represent the same plane curve. We're going to draw up the easiest one possible. So one set of parametric equations for the plane curve defined by y equals f of x is to let x be equal to t and then y is equal to f of t. So literally, this is all we do. We're going to say x equals t every time. And then to get your y equation, all you're going to do is put a t where there was an x. And that's it. So our next one, again, we're going to let x be equal to t. And then what's y going to be? But t squared minus 3. All right. Questions, anybody? Well, I introduced parametric equations talking about throwing something, so it's no surprise that our real application here for parametric equations is projectile motion. So we've already seen that parametric equations are often used to represent the path of a moving object. If t represents time, parametric equations give the location of a moving object and tell when the object is located at each of its positions. Rectangular equations tell where the moving object is located, but do not reveal when the object is in a particular position. That's why parametric equations are preferred for this type of application, because it just provides more information. It gives the when as well as the where. When an object is propelled upward at an inclination theta to the horizontal with an initial speed of v sub 0, the resulting motion is called projectile motion. These are the equations that we use for projectile motion. The x equation is equal to our initial velocity times cosine of theta, t. Don't miss this t here on the end. I know it looks like it's kind of hiding there. So x equals v sub 0 cosine t. And then y is this big long one. Y equals 1/2 g times t squared plus v sub 0 sine of theta times t plus h. G is gravity. So gravity takes on two different numbers depending on whether we're working in US units or the metric units. So if we're in US units, gravity is 32 feet per second, but if we're in metric, then it's 9.8 meters per second. V sub 0 is our initial velocity. H is the height above the horizontal. Sometimes we have an H value and sometimes H is 0. It just depends on the context of the application. So heads up on that. I had a question like this on my last pre-calc exam and people got it wrong just because they used the wrong value for G, that they weren't paying attention if they were in metric or US units. So be sure that you're making sure of that. All right, so Jim, he's going to hit a golf ball with an initial velocity of 150 feet per second, an angle of 30 degrees to the horizontal. The first thing we need to do is find parametric equations that describe the position of the ball as a function of t. So we're going to be plugging into those equations just above. In order to plug into those equations, we need a couple things. We need to know the initial velocity. We also need to know the height off the horizontal, and we need to know which number we should be using for gravity. So we need to pay attention to whether we're in US or metric units. Well, they say our initial velocity is 150. So that tells us our v sub 0. The unit for the velocity is feet per second, which is US units. It doesn't say meters. So that tells us for gravity, we're going to be using 32. And then lastly, it says that we have an angle of 30 degrees. So that's going to be our theta. That's everything we need. Now we're just going to plug it into our equations. X is equal to v sub 0 cosine of theta times t. So let's plug in. It's 150 cosine of 30 degrees times t. So now we need cosine of 30 degrees. Square root of 3 over 2. So this will simplify to x equals 75 square root of 3 times t. Questions at all on getting the x equation? Now we'll do the same thing with y. It's just a more complicated equation. Now, even if we were taking proctored exams, I would not make you memorize this formula. It's possible that your physics instructor might do that, but I'm just teaching you how to apply it here and when we review it again in pre-calc. Oh, we didn't find our h. What's our h value going to be? Any idea? H is our height above the horizontal.
Do you usually graph it and see what like the maximum is?
Well, we need it to be able to plug it in the formula. I can't graph anything if I don't have a y coordinate, right? We need it to be able to plug in this. So he's hitting a golf ball. Where's a golf ball usually at when you hit it?
On the ground.
On the ground, right? So if it's on the ground, then that tells us that our height is going to be 0. Yeah, I know sometimes it's on a tee, but it's not sticking very high off the ground even when it's on a tee. So on the ground, so this tells us that our H value is going to be 0. All right, let's plug in and clean this up. So that's going to be -1/2 times 32t squared plus 150 sine of 30 degrees times t plus 0. That's going to be -16t squared. Sine of 30 degrees is 1/2. Then I don't need that plus 0. So this becomes y equals -16t squared plus 75t. Questions, anybody? All right, well, now we're going to use these equations to answer the rest of the questions. Our first question says, how long is the golf ball in the air? Well, how might we figure that out? Well, let me ask you this first. If the question has to do with how long the ball is in the air, is in the air an X or a Y thing?
Why?
It's a Y thing. So we're going to be working with the Y equation. So I know that right away. So I'm just going to write down my Y equation. All right, I want to figure out how long, so what's the time that the golf ball is in the air? Y represents the, vertical distance. So what might I do to this equation? We've done this before in other math classes outside of the context of parametric equations. If the ball, oh, go ahead.
It's probably wrong, but would you like set x and y equal to each other to see? I
Well,
don't
we're
know.
only going to be using the the Y equation here. We're not using the X equation at all. Well,
I got a quick question.
Yep.
Wouldn't we set y equal to 0 because the ball in the air, it's at 0 when it starts and it should be at 0 when it ends.
That's exactly what we want to do. We're going to let y be equal to 0 because if it's in the air, then that means that there is some sort of y value happening. Some sort of y value happening. And you're exactly right that it's 0 when it starts and it's 0 when it lands. So we're substituting 0 in for y. And then we're going to solve for t. So we can factor here. I'm going to take out a negative t. And then we'll solve each for t. So we get t equals 0 and t equal to 75 over 16. Since it's an application problem, we always want to make sure that our answers make sense for the context of our application. Do both of these answers make sense for the context of the application?
Yes.
Well, so it's now you mentioned that the ball is beginning on the ground, right? So that's before it has become airborne. And that happens when our time is equal to 0. Since the question is not when is the ball on the ground, but how long is the ball in the air, at t equals 0, the ball has not taken off yet. So we do not want to include that solution in our answer because it's not answering the question of how long is the ball actually in the air. We only want the 75 over 16, and then we want to make sure we've answered the question. They're asking us to round to the nearest thousandth. So we'll put that in our calculator. 4.688 seconds. Questions? Does that make sense to everybody why we have to throw out the 0?
Yep.
In part C, they ask us what is the maximum height of the ball. So again, it's talking about the height. So is that going to be our x or our y equation to use?
Why?
Since we're talking height, we're using y again. And we want to find the maximum height. Where would the maximum height occur?
Wouldn't it be at 1/2 of our t from above?
Is it going to be 1/2? Okay, so how do you know it's going to be half the time from above?
Assuming that gravity is a consistent thing and force applied is consistent, it should be halfway through this actual stroke or through the actual through the flight.
He's making it sound so fancy, right? All right, so this y equals, this is a parabola pointing down. So Neil's right. In this example, if you want something that's going to work in every single example, what we're looking for is the vertex of the parabola. So the ball at its max, when is the ball at the max height? That's going to be the x coordinate of the vertex. Because in this particular example, the ball is starting on the ground and then ending on the ground, it is true that the vertex is going to be halfway in between. But there are some applications where it says, you know, you start on a mountain and then you throw it down and then it lands here on the ground. In an application like that, you cannot just cut the flight time in half because you're not starting and stopping at the same like ground level. So because of that, I'm going to choose to do it with the vertex, but if I was really doing it, I would have just cut the time from part B in half. So our t value, it's really t and not x, although we usually think x equals negative b over 2a. So that's going to be negative 75 over 2 times negative 16. We're rounding our answer to the nearest thousand. We end up with our time being equal to 2.344 seconds. And that is indeed half of what we had up here. Part D says determine the distance the ball traveled while in flight. So when it's saying that the distance traveled, when it's talking, oh, somebody hit a golf ball 200 yards, are they talking about the horizontal or the vertical distance traveled?
Horizontal.
It's the horizontal, right? They're not actually like measuring the like how far it actually went up and then down. They're saying how far this way did it go. So in part D here, we're going to be using our x equation, which is x equals 75 square root of 3 times t. I know which equation I'm going to use. How do I figure out the distance that the ball traveled? Well, do we know how long the ball was in flight?
Yeah, from number or letter B, we figured out the time of the flight, so we could just replace that with the original T in the equation.
You got it. So we're going to plug in flight time from part B.
Isn't the flight time from part B the midpoint? So you would want it
No,
from
that
part
was part C,
Oh wait, I'm sorry, I'm on the wrong parts. Sorry.
right? Okay, that's fine. Please ask. All right, that's the total time it was in the air. So we're going to plug that in for T, and that should give us the total distance traveled. I do not have this answer in my notes. Somebody could pop that in their calculator. That'd be great.
I got 608.99.
All right, and then our unit, were we in feet? Yep. There we go. So this may seem like a really, really long number, and you may or may not know much about golf, but golf, they always talk about it in terms of yards. So, I mean, if they said 600 yards, that'd be crazy, but we're saying 600 feet, so that's only 200 yards. That's a reasonable number. Okay, let's check out this other application. Jack launches a small rocket from a table that is 3.36 feet above the ground. So this tells us that we have a height other than 0. Its initial velocity is 64 feet per second. So there is our V sub 0, and also that unit of feet per second tells us that we're going to be using 32 for our G, and it's launched at an angle of 30 degrees. So there's our theta. We want to find the rectangular equation that models its path, and then what type of path does it follow. So basically all you're doing is finding part A in the previous one. So I'm going to put you guys in groups and let you work on it together.